Mars is dead. Its core froze billions of years ago. No magnetic field, no plate tectonics, no volcanic activity. So why is this sitting on its surface? Olympus Mons. The largest volcano in the solar system, more than twice the height of Mount Everest. Built by something that should no longer exist. And why is tiny Io, smaller than our moon, erupting like hell itself? Hundreds of volcanoes. The most volcanic world we've ever found. While frozen Enceladus, so cold it should be geologically dead, shoots geysers of water hundreds of kilometers into space. The solar system's heat doesn't follow the rules. Dead worlds that shouldn't burn, tiny moons that shouldn't erupt, frozen surfaces hiding liquid oceans. To understand why other worlds break the rules, we need to understand how volcanism works on Earth. May 18, 1980, Mount St. Helens, Washington State. A lateral blast traveling 1,050 kilometers per hour. Ash falling across 11 states. 57 people dead. This is what a volcano looks like when everything goes right, or catastrophically wrong. But where does the heat come from? Earth has three sources. Source 1. Primordial heat. Left over from Earth's formation 4.5 billion years ago. When countless impacts turned gravitational potential energy into thermal energy, Earth was molten. That heat is still radiating outward, slowly. Source 2. Radioactive decay. Deep in Earth's mantle, unstable isotopes, uranium-238, thorium-232, potassium-40, break down, releasing energy. This generates about 20 terawatts of continuous heat, enough to power human civilization twice over. Source 3. Tidal heating. Minimal on Earth. The moon's tidal forces are weak, but we'll see why this becomes critical on other worlds. Three sources. Heating Earth from within, driving convection in the mantle. And where that heat reaches the surface? Volcanoes. But Earth has something special. Something almost no other world has. Plate tectonics. Earth's crust isn't one solid shell. It's broken into about 15 major plates, constantly moving at a few centimeters per year, about as fast as your fingernails grow. When plates collide, one dives beneath the other. Subduction. The descending plate carries water, trapped in minerals, locked in sediments. At depths of 100 to 150 kilometers, pressure and temperature increase. The water is released, and water does something extraordinary. It lowers the melting point of rock. The mantle rock, which was solid at 1,200 degrees Celsius, suddenly melts at 800 degrees Celsius. Magma forms. Less dense than surrounding rock, it rises, and eventually, it erupts. This is why the Ring of Fire exists. Subduction zones circling the Pacific. 75% of the world's active volcanoes. Earth also has hotspot volcanoes, like Hawaii, where mantle plumes from deep within the Earth punch through the crust, regardless of plate boundaries. But in both cases, the engine is the same. Internal heat plus plate tectonics equals volcanoes. Here's what we expected for the rest of the solar system. Small worlds equals cold. The smaller the planet, the higher its surface area to volume ratio. Heat escapes faster. Mercury, the Moon, Mars, all smaller than Earth. We expected them to have cooled billions of years ago. their interiors frozen, their volcanism extinct. And moons? Even worse. They're tiny, far from the sun. No internal radioactive heating comparable to planets. They should be frozen solid, geologically dead. So explain these. Olympus Mons on dead Mars. Io erupting non-stop. Enceladus shooting ice geysers. The rules we just established? The solar system ignores them. Let's find out why. Olympus Mons. 600 kilometers in diameter, roughly the size of Arizona. 22 kilometers high above the Mars datum, the equivalent of sea level on a waterless planet. Mount Everest? 8.8 kilometers above sea level. Olympus Mons is 2.5 times taller. At its summit, a caldera 60 by 80 kilometers across. 6 overlapping collapse craters where magma chambers emptied and the ground collapsed. Layer upon layer of basaltic lava flows, built over hundreds of millions of years. Olympus Mons isn't a mountain, it's a shield volcano, like Hawaii's Mauna Loa, but vastly larger. And it's been extinct for at least 25 million years. Probably longer. So why is it so big? The answer lies in what Mars doesn't have: plate tectonics. On Earth, the Pacific plate moves northwest at about 7 centimeters per year. As it drifts over the Hawaiian hotspot, new volcanoes form. Kauai, Oahu, Maui, the Big Island. Each volcano gets a few million years of activity before the plate carries it away from the magma source. Result? A chain of progressively younger volcanoes, none too large. Mars has no plate tectonics. Its crust is a single stationary shell. The Martian equivalent of a Hawaiian hotspot, a deep mantle plume, stayed in one place for hundreds of millions of years. Lava flow upon lava flow, same location, building upward. And because Mars's gravity is only 38% of Earth's, the volcano could grow taller before its own weight caused it to collapse. The lack of plate tectonics is why Olympus Mons is so big. But it doesn't explain why it existed at all. Mars should have been dead long before Olympus Mons formed. September 2024, Europlanet Science Congress, Berlin. Dr. Bart Root of Delft University of Technology presents new gravity data for Mars. The Tharsis region, home to Olympus Mons and 3 other giant volcanoes, shows a gravity anomaly. It's higher than average Mars, much higher, but surrounded by a ring of weak gravity. That's strange. Dense volcanic rock should create strong gravity, not weak. Root's team calculated what could explain the anomaly. A light mass, about 1,750 kilometers across. At a depth of 1,100 kilometers, a massive plume of hot, buoyant mantle material. Still there, still active, rising toward the surface. NASA's InSight mission detected Marsquakes in the Tharsis region, seismic evidence of ongoing mantle activity. Root. It shows that Mars might still have active movements happening inside it, affecting and possibly making new volcanic features on the surface. Olympus Mons is dormant, not dead. Its last major eruption was likely 25 million years ago, geologically recent. And beneath it, a plume that might still be feeding it. Mars's volcanism lasted far longer than it should have. Primordial heat? Mostly gone. Radioactive decay? Weaker than Earth's. Mars is smaller, less radioactive material. But mantle convection? Still happening. Barely. Just enough to create a plume beneath Tharsis. Olympus Mons exists because Mars isn't quite as dead as we thought. It's dying, slowly. But the fire hasn't gone out yet. And then there's Venus, Earth's twin, which never stopped burning at all. Venus, 85,000 volcanoes. Let that sink in. 85,000. Earth has about 1,350 potentially active volcanoes. Venus has 63 times more. Shield volcanoes like Mons and Mons, pancake domes, flat, viscous lava structures unique to Venus. Vast lava plains covering 65% of the surface. Venus is the most volcanic world in the solar system by sheer number. And unlike Mars, Venus is still active. NASA's Magellan mission mapped Venus from 1990 to 1992. For over 30 years, that data sat in archives. Then in 2023, scientists went back and looked again. March 2023. Dr. Robert Herrick at University of Alaska Fairbanks compared Magellan radar images taken 8 months apart in 1991. A volcanic vent near Mons, near Venus's equator, had changed. The vent expanded by nearly 2 square kilometers. Lava had filled the crater and spilled down the slopes. Direct evidence of an eruption during the Magellan mission. May 2024, Italian researcher Davide Solcanese analyzed different Magellan data. He found 2 more eruption sites: Mons in Istla Regio, western Niobe Planitia, home to numerous shield volcanoes. Between 1990 and 1992, radar signal strength increased in both locations, indicating fresh lava flows, new rock forming on the surface. The Mons eruption produced about 12 square kilometers of lava, enough to fill 36,000 Olympic swimming pools. For comparison, Mauna Loa's 2022 eruption on Earth produced enough lava to fill 100,000 pools. Venus's eruptions are significant, ongoing, real. Venus and Earth are twins. Similar size, similar mass, similar composition, formed at the same time from the same material. But their surfaces couldn't be more different. Earth, plate tectonics, oceans, life. Venus, 470 degrees Celsius surface temperature, 92 atmospheres of pressure, sulfuric acid clouds, no plate tectonics. But both are still volcanically active. Why? March 2025. Slava Solomatov and Chavi Jain at Washington University publish research in physics of the Earth and planetary interiors. Their conclusion: Venus's crust itself might be convecting. Venus's crust is 30 to 90 kilometers thick, much thicker than Earth's. At Venus's extreme surface temperatures, 870 degrees Fahrenheit, 465 degrees Celsius, and with heat from below, the base of the crust reaches supersolidus temperatures, hot enough to partially melt. The crust becomes mushy, convective, churning. Without plate tectonics to shed heat, Venus needs another mechanism. Crustal convection might be it. Heat from the mantle rises through the churning crust, creating localized melting and volcanism. 85,000 volcanoes. Venus doesn't have plate tectonics, but it has something else. A crust, hot enough to flow, to convect, to bring magma to the surface in thousands of locations. Venus burns because it's too hot to stop. Mars burns because it's not quite dead. And then there's Io, which burns for a completely different reason. Io, Jupiter's innermost large moon, slightly bigger than Earth's moon. Over 400 active volcanoes, lava lakes, sulfur geysers erupting 300 kilometers into space. Surface temperatures exceeding 1,800 Kelvin, hotter than most Earth volcanoes. Io produces more volcanic heat per unit area than any other world in the solar system. 60 times more than Earth. More volcanic activity than every other world combined. And it shouldn't exist. Io is tiny. It's far from the sun. It should have frozen solid billions of years ago. Instead, it's the most volcanic world we've ever found. Why? The answer is gravity, but not the way we saw in episode 2. This time, gravity isn't sculpting, it's squeezing. Io orbits Jupiter once every 42.5 hours, but it's not a circular orbit. It's elliptical, eccentric. Eccentricity, 0.0041. Sounds tiny. It's enough. When Io is close to Jupiter, perigove, Jupiter's gravity is stronger. Io gets stretched into an oval, a tidal bulge. When Io is far from Jupiter, apogee, the bulge relaxes. Close, stretch. Far, relax. Close, stretch. Far, relax. Over and over. Billions of times. Every squeeze generates friction. Rock bends, cracks, grinds against itself. Friction converts gravitational energy into heat. A lot of heat. Io generates 2.5 watts per square meter. Internally generated heat, not from the sun. Earth generates 0.09 watts per square meter from radioactive decay and primordial heat. Io generates 28 times more heat per square meter than Earth. Tidal heating. It's the third source of planetary heat. And on Io, it dominates everything else. But wait. Orbits naturally circularize over time due to tidal friction. If Io's orbit became circular, the tidal bulge would stop changing. No more squeezing, no more heating. So why hasn't Io's orbit circularized? Orbital resonance. Io completes one orbit for every 2 orbits of Europa and every 4 orbits of Ganymede. 1 to 2 to 4. Perfectly locked. Every time Io passes Europa, Europa is in almost the same position. Europa's gravity tugs on Io. These periodic tugs pump energy into Io's orbit, maintaining its eccentricity. Europa and Ganymede prevent Io's orbit from circularizing. They keep Io locked in its elliptical path, forever squeezed, forever heating, forever erupting. Io didn't choose this fate. It's trapped. (2024) NASA's Juno spacecraft makes 2 close flybys of Io, the closest in over 20 years, and discovers something unexpected. Previous models predicted a shallow global magma ocean beneath Io's crust. Molten rock everywhere, just below the surface. Juno's gravity measurements proved otherwise. Io's interior is mostly solid, not a magma ocean. Instead, there's a partially molten asthenosphere, a squishy layer about 50 to 100 kilometers below the surface, where rock is only partially melted. Tidal heating is concentrated where tidal stresses are strongest, the equator. But magma finds pathways wherever the lithosphere is weak. Hence volcanoes at the poles too, just less powerful. Io isn't a ball of liquid rock with a thin crust. It's a solid moon being constantly kneaded by Jupiter's gravity, with a partially melted layer that never gets a chance to cool. Tidal heating doesn't melt Io from within. Tidal heating makes Io melt itself through friction. Over and over. Forever. Enceladus. Saturn's sixth largest moon, 500 kilometers in diameter, about the width of Arizona. Surface temperature, minus 198 degrees Celsius, 75 Kelvin. And from cracks near its south pole, called tiger stripes, geysers erupt. Water vapor, ice particles, organic molecules, salt. Shooting 300 kilometers into space. In 2005, Cassini flew through one of these plumes and sampled it directly. Water, carbon dioxide, methane, ammonia, sodium chloride, table salt, and complex organic molecules. This is not volcanic eruption in the traditional sense. This is cryovolcanism. Ice volcanism. And it's coming from a moon that should be frozen solid. Beneath Enceladus's 20 to 30 kilometer ice shell lies a global ocean of liquid water. We know because Cassini measured Enceladus's gravity field and detected mass anomalies consistent with a dense liquid layer. The tiger stripes are fractures in the ice shell, where the ocean below can reach the surface. 101 individual geysers have been mapped, all originating from these 4 main fractures. But here's the mystery. How does ocean water make it through 20 to 30 kilometers of ice? February 2025. Colin Meyer at Dartmouth publishes new research. His proposal: the geysers don't come directly from the ocean. They come from a mushy zone in the ice shell itself. Tidal forces from Saturn create friction along the tiger stripe fractures, shear heating. The ice shell contains salts. Salts lower the melting point. Localized heating causes partial melting. A slush of ice crystals and liquid brine forms within the fractures. When the fractures open due to tidal flexing, the pressurized brine escapes. As it hits the vacuum of space, it instantly boils and freezes, creating the plumes we see. Cassini observed that plume brightness varies with Enceladus's orbital position. When Enceladus is farthest from Saturn, tidal stresses open the fractures wider. More material erupts. When it's closest, fractures compress. Less eruption. Enceladus is being squeezed by Saturn, just like Io is squeezed by Jupiter. But instead of rock melting, ice melts. Instead of lava, water. Same mechanism, different material. The material ejected from Enceladus doesn't fall back. Most of it escapes into space and becomes part of Saturn's E-ring, a faint, diffuse ring fed by Enceladus's geysers. But some falls back as snow. Enceladus is burying itself in its own ejecta, building a layer several hundred meters thick. And what Cassini found in the plumes? Organics, salts, silica nanoparticles, indicating hydrothermal activity on the ocean floor. Everything life needs. Liquid water, check. Energy source, hydrothermal vents, check. Organic molecules, check. Salts and minerals, check. Enceladus is frozen on the outside, but inside, a warm ocean, possibly with hydrothermal vents, possibly habitable. And we didn't even need to land to sample it. The ocean comes to us. NASA and ESA are planning missions to Enceladus, to fly through the plumes again, to analyze the chemistry in detail, to answer one question: is there life in Enceladus's ocean? We've seen three types of volcanism, three sources of heat. Mars, primordial heat plus radioactive decay, almost exhausted. But a deep mantle plume beneath Tharsis keeps Olympus Mons fed. Barely. Venus. Same heat sources as Mars, but Venus is bigger. More radioactive material, more primordial heat. Plus crustal convection at extreme temperatures keeps 85,000 volcanoes active. Io and Enceladus. Tidal heating. Orbital resonances lock them into eccentric orbits. Gravity squeezes them billions of times. Friction generates heat. Rock melts on Io. Ice melts on Enceladus. Three heat sources. Primordial, left over from formation. Radioactive, unstable isotopes decaying. Tidal, gravitational squeezing. Every active volcano in the solar system is powered by at least one of these. The solar system doesn't follow our intuition. Small doesn't mean cold. Dead doesn't mean extinct. Frozen doesn't mean inactive. Mars hides a plume beneath its largest volcano. Venus has a crust hot enough to convect on its own. Io is eternally squeezed by Jupiter, turning orbital energy into volcanic hell. And Enceladus hides a warm ocean beneath a frozen shell, venting it into space. Heat finds a way, even when it shouldn't exist. What we've learned about tidal heating changes everything. We've discovered thousands of exoplanets. Many orbit close to their stars, tidally locked, one face always toward the star. Those planets experience tidal forces far stronger than Io or Enceladus. If tidal heating can create volcanism on a moon 500 kilometers wide, what could it do to an Earth-sized planet locked to a red dwarf? And in our own solar system, we're finding ocean worlds everywhere. Europa, Ganymede, Enceladus, maybe Titan, possibly Mimas, all heated by tides, all potentially habitable. The search for life isn't just about finding water, it's about finding heat, and tidal forces provide heat almost anywhere. But heat doesn't just create volcanoes, it creates weather. And the solar system has weather unlike anything on Earth. Storms larger than planets, winds faster than sound, methane rain, lightning 10 times more powerful than Earth's. The atmosphere is the next battlefield. This is Cosmic Canvas, where we reveal the forces that shape worlds. Fire and ice. Opposite sides of the same coin, both driven by heat, both defying expectation. Until next time, remember that nothing in space is ever truly dead. It's just waiting for the right force to wake it up.